Hello, folks. All right, so in this video, we're going to continue with grade 12 statistics. So we'll be looking at curve fitting, right? In grade 11, we used various means such as histograms, frequency polygons, and ogives to visualize our data. These are very useful tools to depict univariate data, meaning data with only one variable, such as the height of learners in a class. Last year, we also learned about a visual tool called scatter plots. Scatter plots are a common way to visualize bivariate data, meaning data with two variables. This allows us to identify the direction and the strength of a relationship between two variables. We identify the nature of a relationship between two variables by examining if the points on the scatter plot conform to a linear, exponential, quadratic, or some other function. The process of fitting functions to data is known as curve fitting. The strength of a relationship can be described as strong if the data points conform closely to a function, or weak if they are further away. In the case of linear functions, the direction of a relationship is positive if high values of one variable occur with high values of the other, or negative if high values of one variable occur with low values of the other. All right, so now let's look at the different relationships. So we have a strong positive linear relationship. This is a strong positive linear relationship and a strong negative linear relationship. This is a weak positive linear relationship and an exponential relationship. This is a quadratic relationship. Here, there's no relationship. Right. So let's look at examples. So examine the scatter plot below of data collected from a new shop. This is our scatter plot. So number one, what are the two variables being compared? What type of function best fits the data? The relationship between the two variables, strong or weak? Is it positive or negative? Describe the relationship in one sentence. So the variables being compared are average daily number of customers and time in months. The data fit an exponential function. The data points appear to fit the curve closely to perfectly, so the relationship can be described as very strong. As time increases, the number of customers increase, so the relationship can be described as positive. There is a very strong positive exponential relationship between average daily customers and time in the new shop, right? So in the worked example above, by plotting the average daily customers and time data of a new shop on a scatter plot, we were able to identify the relationship between the two variables. Once we know the relationship between two variables, we are able to do another very useful thing. We can predict values where no data exists. Okay, so this takes us to definitions of two important terms, interpolation and extrapolation. When we predict values that fall within the range of our data, so they fall within, this is known as interpolation. When we predict values of a variable beyond the range of our data, so beyond the range of our data, this is known as extrapolation. Extrapolation must be done with caution unless it is known that the observed relationship continues beyond the range of our data. For example, an exponential function may look linear if we only have the first few data points available, but if we extrapolate far enough beyond the initial data points, our prediction will be inaccurate. In order to interpolate or extrapolate values, we need to find the equation of the function which best fits the data. For linear data, we draw a straight line through the data which best approximates the available data points. This line is known as the line of best fit or trend line. Let us try our hand at this in the following example. So, use the data below to draw a scatter plot in the line of best fit. Write down the equation of the line that best seems to fit the data. Use your equation to calculate the estimated value for y if x is 4, then if y is 6. So these are some important things when you draw your graph. Now this is how the graph looks like. All right, these are your points. Then, now the next step is to draw a line which goes as close to as many points as possible. It is generally best to have as many points above the line as below the line, right? So if you have 3 above, then 3 below. Now, from the graph we have drawn, we estimate the y-intercept to be 1.5. We estimate that y is equals to 3,5 when x is equals to 3. So we have that point, we have these points. The gradient on the line M is given by this equation, which gives us 2/3. So we finally have the equation of the line of best fit as y is equals to 2/3 x plus 3/2. All right. So the equation of the line is y is equals to 2/3. So in order to find the unknown, we just insert x. So if you plug x there, then this is our value. Since this x value is within the data range, this is interpolation. Whereas for y, because y is outside the data range, this is extrapolation. Right. Okay, folks, I'll pause the video. Please try the exercise. Pause the video and do the exercise. That's the only way for you to learn. You won't benefit much from just watching the video passively. So All right, folks. I hope that you tried the exercise. So A, quadratic. B is exponential. C, you can see that it's linear, negative, linear. And D is linear as well, but this one is positive, it's increasing. E, it's exponential. And F, it's quadratic. All right. Then for number 2, the data fits a strong positive linear function. Yeah. Right. Then draw a line of best fit. So what is important here is that the method is more important than the final answer. So you need to pay special attention to the y-intercept of the line of best fit. Right. So then obviously for C, it will depend on your answer to the questions above and D. Then number 3, this question about TP, it's exponential. And then B, we are told that x sub 0 is 2 and t is equals to 24 and r is 1. I just plug those things there. Then you get your answer. Okay. Then number 4, quadratic. Right, so Marellis determines that the equation for the function is this. Determine the optimal temperature. The optimal temperature is the turning point of the function. Now, since this is quadratic, we find the equation of axis of symmetry because it gives you the x coordinate of the turning point. And then once you get that, you substitute to your equation to get the y coordinate. Or another way is to take the derivative, the first derivative of the equation for the function and then equate it to 0. Right? Yeah. Then you equate that thing to 0 and solve for x. Now you can substitute to the original function to get your y. Therefore, the optimal temperature to grow wheat is 18.33 degrees Celsius and respective crops yield is 6.17 tons per hectare. All right, so for this one, that's your scatter plot. You can see here it's strong. Yeah, the data shows a strong negative linear relationship. See? There we go. Then those ones, they'll obviously depend on what you have. All right. In the previous worked example and exercises, you drew the line of best fit by hand. This can give us a reasonable approximation of which function best fits the data when the data points are close together. However, you and your classmates may have found that you obtained slightly different answers from one another. In the next section, we will learn about a more precise way of fitting a linear function to data. We'll look at linear regression now. So linear regression analysis is a statistical technique for finding out exactly which linear function best fits a given set of data. We can find out the equation of the regression line by using an algebraic method called the least squares method, available on most scientific calculators. The linear regression equation is written this way. We say y hat, right? So that's y hat, or y is equals to a plus bx. Of course, these are both variations of the more familiar equation, y equals to mx plus c. The least squares method is very simple. Suppose we guess a line of best fit, then at every data point, we find the distance between the data point and the line. So find the distance between data point and the line. If the line fitted the data perfectly, this distance would be 0 for all the data points, obviously. The worse the fit, the larger the differences. We then square each of these distances and add them all together. So the best fit line is then the line that minimizes the sum of the squared distances. So suppose we have a data set of n points. We also have a line f of x equals to mx plus c that we are trying to fit to the data. A distance between the first data point and the line, for example, is y sub 1 minus f of x 1. And then we now square each of these distances and add them together. Let's call this sum S of MC. Then we have this, right? That's our problem, is to find the value of M and C such that S of MC is minimized. Let us call these minimizing values B and A, respectively. Then the line of best fit is f of x is equals to a plus bx. You can find a and b using calculus, but it is tricky, and we will just give you the result, which is that. Look at that thing. Look at that thing. Okay. So let's look at an example so that you can understand how this thing actually works. In the table below, we have the records of the maintenance cost in rands compared with the age of the appliance in months. We have data for 5 appliances. Determine the equation of the least squares regression line by hand. So these are appliances. All right, then the total. So that is X, that is Y. And then multiply X and Y, and you square Y. From there, you substitute now. Look, for B, N is 5. Then multiply by the sum of XY, which is 23, minus the sum of X is 80, times the sum of Y, which is 1650, over N times the sum of X squared is 1650, minus the sum of X to the power of 2. So the sum of X is 80, then you square that. So that gives us 12. Right? So we have A is equals to Y minus BX. So this is equals to, our Y is 1160. Oh, Y bar, remember what this means. Y bar tells us that this is the mean of Y. So remember, you sum all those numbers, then you divide by the number of items that you have. So it's 1160 divided by 5 minus, we already know B to be 12. And then now multiply by the mean for the data set of X, which is 80 over 5. And that gives us 40. So Y is equals to 40 plus 12X. Now let's use the calculator to find the equation of the least squares regression line for the following data set. If you have a Casio calculator, do the next worked example first. Come back to this worked example once you are done and see if you get the same thing. Okay. Let's see. With the Casio calculator, let's see if all right, folks. So now we want to try and use our calculator to do this thing. Right. So using a calculator, determine the least squares line of best fit for the following data. So it's mode. Then after mode, I'll select 3, which starts, then 2. Then my data set, so that is 52 equals to 55 equals to 86 equals to 71 equals to 45 equals to, then Y we have 48, 48, 64, 64, 95, 79, 50. Right. Then AC and shift 1. Reg, we're looking for reg 5. Now you see, depends on what we're looking for first. So what are we going to start with? Let's see. Start by finding A. So 1 equals to, there's A. Right. Then B, shift 5. B is 2, 1,17. Right. So yeah. Okay then. So again, folks, I'm going to pause the video, try this exercise, and then we will continue when you're done. Then number three. All right, folks. So here's the answer for this question. Right. Mhm. Then B. Mhm. And C. Mhm. Then number two. A. That's that. Then there we go. There we go. There's your proof. And number four. A. That's your scatter plot there. And B. Those are your numbers. And C. Y is equals to 858,48 plus 164,06x. And D is that's E. And then that's that. Then this. Mhm. Number six. It's your point. Mhm. Yes, that is your line. Hmm. Now that we have a precise technique for finding the line of best fit, we still do not know how well our line of best fit really fits our data. We can fit a least squares regression line to any bivariate data, even if the two variables do not show a linear relationship. If the fit is not good, our assumption of the A and B values in y hat equals to A plus bx might be incorrect. Next, we will learn of a quantitative measure to determine how well our line really fits our data. So that takes us to correlation. So the linear correlation coefficient R is a measure which tells us the strength and direction of a relationship between two variables. The correlation coefficient R, which is between -1 and 1 inclusive, when R is equals to -1, there is a perfect negative correlation. Right? When R is equals to 0, there is no correlation. And when R is equals to +1, there is a positive perfect correlation. This is positive, strong. The coefficient is around 0.9. Here it's 0.7. Here it's 0.4. Then negative and fairly strong, that is approximately negative 0.7. And here there's no correlation here. The linear correlation coefficient R can be calculated using the formula R is equals to B, right? Where B is the gradient of the least square regression line. And then this is standard deviation, the X value of the standard deviation, and the Y value of the standard deviation. This is known as the Pearson's product moment correlation coefficient. It is much easier to do on a calculator where you simply follow the procedure to calculate the regression equation and go on to find R. So in general, these are some of the things that you're gonna have to remember. If R is 0, then we have no correlation. Then if R is between 0.5 and 0.25, the strength is weak. Same applies to negatives. For moderate is 0.5 and 0.75. Strong is 0.75 and 0.9. Very strong is 0.9 to 1. And then perfect correlation is when we have 1 or -1 the other side. Note, correlation does not imply causation. Just because two variables are correlated does not mean that they are causally linked. Meaning, if A and B are correlated, that does not mean A causes B or vice versa. This is a common mistake made by many people, especially journalists looking for their next juicy story. For example, ice cream sales and shark attacks are correlated. This does not mean that the sale of ice cream is somehow causing more shark attacks. Instead, a simpler explanation is that the warmer it is, the more likely people are to buy ice cream and the more likely people are to go to the beach as well, thus increasing the likelihood of a shark attack. So let's look at an example. A cardiologist wanted to test the relationship between the resting heart rate and the peak heart rate during exercise. Heart rate is measured in beats per minute The following set of data was generated from 12 study participants after they had run on a treadmill at 10 kilometers per hour for 10 minutes. All right, so from there, we're going to draw a scatter plot for the data, then find the equation of the line of best fit, then do some estimations, calculate the correlation coefficient, and then the relationship. So there we go. That is what we have there. Then calculate the equation of the line of best fit. That's that. Okay, calculate the estimated value for y if x is 70. That is that. Now calculate the correlation coefficient. So the formula for R is this formula, right? We already know the value of B, and you know how to calculate B by hand from worked example 5. So we are just left to determine the value for standard deviation of values of X and standard deviation of values of Y. The formula for standard deviation is this. We also learned about this in our previous lesson. So first you need to determine the mean of X values and the mean of Y. Then complete the table. So that is that. So you take each data point, then you subtract the mean from it. Right. So yeah, that's that. So once you know the method for finding the equation of the baseline of each on your calculator, finding the value of R is trivial. After you have entered all your X and Y values into your calculator in step mode, on the Casio calculator, press Shift, then start 5, 3, then equals 2. Now comment on the correlation coefficient. Therefore, there is a strong positive linear relationship between resting heart rate and peak heart rate during exercise. This means that the higher your resting heart rate, the higher your peak heart rate during exercise is likely to be. Okay, folks, it's that time. Please pause the video and attempt the exercise. Right, folks. So we're back at it. This is that, and what is that? Therefore, the correlation between X and Y is negative but weak. As you can see, it's less than 50. It's less than negative 0, comma, sorry. Those are some rough calculations. This one is positive and moderate, 0.68. Then, so here, this one is 0.91, so it's positive and very strong. Okay, is that, that, then number 4, that's that. Then mhm, mhm, then number 5, yes, mhm, mhm, yes, mhm, All right, folks, we're going to end this video with the end of chapter exercise. So please go through it, then you'll find solutions from the Siyavula website. All right, thank you so much, folks. Goodbye. See you in the next video.